Hello, welcome to another problem session. Today we'll do a concept of moment of inertia. I'm going to go deeper today. We'll do some example problems, but here you really need to know the process and what it to understand what it really represents. So, moment of inertia comes up in rotation, and when you examine motion of body going, say, something going in a circle about an axis, so it's kind of circular motion. You can think of a circular motion of mass m. You can look at it as a linear motion where if its velocity is v that way, and from the center of this axis is a distance r that way. So you can examine it in terms of the angle is covering, or in terms of the distance is covering. But if you think in terms of angle is covering, we say that interpretation is a rotation problem. So in the rotation, we pick some arbitrary place which is fixed, and this thing is the direction in which the object is. That's the theta. So we define using these how rate or angle changes, assign a direction in that way, and we say d theta dt, this direction which is perpendicular to the angle I'm looking at, say this is axis direction, and that's called angular velocity vector. And when we look at a vector called this r vector and p vector, so if I look at this r cross p of this object, then it can be written completely in terms of the angle, and you can see v. We look at the velocity vector and this r vector, then actually it comes out like omega cross r is equal to the velocity vector. So this was proven some time ago, some previous lectures. So this is r cross m omega cross r, and when you expand this, you can collect terms where it's kind of like a something along I hat plus something along j hat plus something along k hat. You can write like that, and so this is a new vector, and we call it angular momentum vector. You can write these in terms of this components omega. So omega has omega x, omega y, omega z. This is the component of this vector. Then you can actually write this whole thing like this will be something I xx omega x plus I xy omega y plus I xz omega z, and that's the I hat. Plus j hat, very similar, I yx omega x plus I yy omega y plus I yz omega z j hat, plus a similar thing, I zx omega x plus I zy omega y plus I zz omega z. And these i's just corresponds to how the just m and r So this like I xx, for instance, is just m y square plus z square. We have just one mass. I xy equals to minus m xy. And other, you can actually pretty much guess what the others will look like. So Iyy is going to be the x square plus z square, right? M x square plus z square. Ixz equals to minus m xz, and yz is minus m. So yx will be minus mxy. It is symmetric, and yz equals to minus myz, and zz is going to be again made of the other two, x square plus y square, and zx will be just minus m z and x, which is the same as that, and zy equals to same as that, yz. Okay. In this situation, if I just call this a z-axis, and let's call this x-axis, and somewhere there is a y-axis. If those are my axes, then you can see in this situation z equal to 0, and omega is only omega z z hat, meaning omega x is 0, omega y is 0, so those are 0. So since z is 0, and if you go in here, angular momentum, we don't need this, 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 we don't need this. So this is k hat. So here L simply becomes I x z omega z I hat plus I y z omega z j hat plus I z z omega z k hat. Now if I look at using z equal to 0, this will be 0 for xz. This will give me 0, and this will give me 0. So this is 0 here in this example, and this is also 0 in this example. So here angular momentum is also omega is that way, and angular momentum is that way. So angular momentum is just simply Izz omega z k hat. So this is quite easy to get. Izz here was just this x square plus y square. So when I look at this mass, its x and y and the z is 0. In this choice of the coordinate system, it's just simply this is the radius of the circle, the radius r. So this is m r square omega z k hat. So this is the only of all the moment of inertia different these i's are all the moment of inertia. Ij are called components of moments, the components of moment of inertia, right? Of all of them, the only one I needed was Izz, and that's actually a lot of simplification. So to recap, we have a situation where a point mass m is going in a circle, and this is my z-axis, and this is my x-axis, this is my y-axis, and this is at angle theta. So this is omega direction, and we found that IZZ is the only one I need, and that was M, and this distance is R square, and L just turns out to be IZZ omega Z hat. Okay, so there are some axes in which things just very simple, right? If I have some object which is kind of odd shape, and is rotating about that, then if I pick this is the omega direction because it's rotating about that, then if I pick just arbitrary axis, so if I pick this, say this is Z axis direction, and there's some X direction and some Y direction, I will find that omega is omega Z hat, right? But L will be I ZX, XZ omega Z in the X hat direction plus I YZ omega Z Y hat direction plus I ZZ omega Z hat direction. And unlike over here, these are not zero anymore. These are not zero anymore. If X, Y, Z, some arbitrary directions. However, there's particular directions in which called principal axis. However, if X, Y, Z axis towards principal axis, so this is a special axis, principal axis. Later on you will learn how to find them in an arbitrary case when you do linear algebra or more advanced mechanics class. So when you have principal axis, then this IXZ is 0, IYZ is 0, and IXY is 0. So the only one left will be only non-zero, and some only non-zero will be IXX, IYY, and IZZ. So these are sometimes called this level as I1, this one we can call it I2, this one we call it I3, and so these are principal moment of inertia. These are principal moment inertia, and this is what we normally do. So if you have a for instance, if you have a cylinder, then principal axis will be, there will be one principal axis, and this will be another principal axis, and this will be another principal axis. So you can call it X, Y, and Z. These will be principal axis. So by symmetry, you can actually tell which directions will be such that if you compute this off diagonal, they're called off diagonal moment of inertia. So these are off diagonal, these are diagonals, and this will be off diagonal. So which one will be zero, which will be non-zero? Okay. So let's look at an example calculations. So can do examples. So if I have a look at a thin rod, in the thin rod, so all the masses along one axis. So this thin rod, and we can forget about the y and z direction. So if I look at symmetry, I should have one axis along this direction. So let's call this x-axis. Long axis, we're gonna call it z, okay? Long z. And let's call this x-axis, and let's call that y-axis. Okay. So these are the principal axes. And I want to find moment inertia, say I, zz. So if I go, I break it up at a small elements, just like we do center of mass, right? So this is, if you look at all of these coordinates, x is 0, y is 0, and it's some point z equal to z, and this is dz. So look at this, how much mass there is. So this will be for, if I write down the whole thing, it becomes an integral, right? Integral dm times x square plus y square for zz. And if I xx would be same kind of integral, dm will be how much mass is there in the dm, mass here. And this, to set it up dm, I will have, because I'm in xx, I'll get a y square plus z square. I need to do this integral, and Iyy will just integrate dm x square plus z square, x square plus z square. Okay. And so what's this dm? Dm is, there must be some density, rho, kilogram per meter, because I'm on a linear thing. So this will be rho times dz. So that's what this will be. Now over here, x is 0, y is 0 for every element. So this actually is just 0. And it reflects the fact that if I rotate about this, none of the masses are off axis, you know. So how about this guy, dm over here is, let's do it over here, more space. So dm is going to be rho dz, and y0 z square. So if I do this integral z over z, so the z in here can go from minus L over 2 to L over 2. So minus L over 2 to L over 2. So I've got a rho, and I have even integral to 2 times 0 to L over 2 z squared dz. And so 2 times rho, 1 over 3 L over 2 square. So what, cube, I think, cube, yeah. And so bottom is 24, so I get 1 over 12 rho L, which will be the total mass, times L squared. So 1 over 12 m L squared. So that's I xx. If you do this, it will be exactly the same thing actually. Again, the rho dz for this, the x is 0 plus z square, and the same range, exactly same integral, so I don't need to do it, 1 over 12 ml square. So I set this up, but you can see from the symmetry, if I rotate, this IXX will go with this, and then IYY will go with this, and the situation is completely symmetric. The whole rod is going around, and this whole rod is going in that way. So I could have said this equals the same. So I got, if I want the moment of inertia about any direction, you know, so if I took the rod and actually rotate about this axis. So suppose I rotate about this axis, so I'll have an omega, and that I can break into x, y, and z directions. So L will be I xx omega x x hat plus I yy omega y y hat plus I zz omega z z hat. So because we found them, I can actually study rotation about any arbitrary direction very easily. So this is 1/12 ml square omega x x hat plus omega y y hat, because this is 0 for a thin rod. So you can see that this may be arbitrary direction, but L is in this direction. So L is not necessarily parallel to omega, you know, if I rotate about arbitrary direction. But if I rotate about rotate about this direction, say rotate about this x direction, then if you just looking at this, if you rotate about x direction, then L, in this case, L is simply going to be I xx omega x I hat, since omega y is omega z is 0. If this is x direction, so omega is in that direction. So omega is only omega x x hat. So if I rotate about principal axis, so if rotate about principal axis, then L is parallel to omega. And so many of the times we're going to study the problems where I'm going to just rotate about the principal axis. So principal axis important. Okay. Another thing that's important is when you are let's do another example. So if I have a ring, so here is the ring, and what's the principal axis for this? Principal axis. So that's the first thing you should ask. So from the symmetry, it will be one of this axis, and then you'll have two of these axes go like that. So if I call it x-axis, y-axis, and z-axis, well, so I just need to find izz, ix, xx. This should be equal to iyy from symmetry. Okay. So what izz? So izz is integrate, take a dm, and x squared plus y squared. Okay. So we'll take a small element as the dm. And let's call it this a radius r. So this actually r squared here for every element, x squared plus y r squared. So this is just equal to, and this is constant, so r square comes out. So and dm is just basically adding up all these masses, so I really don't have to do any integrals. So r square total mass mr square. So izz is like trivial here. How about ixx? Well, we start same way, and so let's look at a ixx. Ixx will be dm, and this time it will be y square plus z square. Of course, z is equal to 0 here because all in over here. So this just becomes dm y square. Okay, one way to do this dm will be write dm and y square is because this angle, we can look into the angle. So this, let's convert that into d theta, and this will be theta. So if I look at it, let's take it over here so that it's easy to see it with respect to x-axis. So let's call d theta here, and so y will be for this, y will be this guy, which means is quick sine theta, right? So y equals to r sine theta, and dm is the arc radius r d theta, so times rho, and rho is kilogram per meter. So now putting in here, I'm going to get a r d theta r square sine square theta, and to get all the masses, I'm going to have to go 0 to 2 pi in the theta. R square sine theta and rho is the density. Okay, so I have a rho r cube 0 to 2 pi sine square theta d theta. Okay, doing this not that hard, but requires a trick. 0 to 2 pi 2 sine square theta d theta, and then I can do it in a double angle. So this will be 1 minus cosine 2 theta, and so if I integrate over that, I'm going to get a 0 because I can go 2 cycles of cosine. So, and this one's give me half times 2 pi plus 0, and this is going to just give me pi. So I got a rho r cube times pi. Mass is, I go all the way around at the rim, so mass is 2 pi r rho. So from there I get a half m r square. So I got ixx is this, so that should be equal to iyy. So trying to write the, say, if I rotate about this axis, so say omega is this, omega 1 is that, which is omega 1 z hat, then L1 will be like that. L1 will be that L1 vector will be mr square omega 1 z hat. If I rotate about the y-axis, let's call this, I'm going to rotate with a omega 2 vector. So L2 will be m r square. I'm going to have this will be I y omega 2 y hat. However, if I rotate about some arbitrary axis, so I rotate about this axis. So I'm going to rotate about this axis, means omega this, say arbitrary, omega arbitrary. So omega arbitrary will just become some omega x hat plus omega y hat, just like any vector, right? So just like a vector decomposition, you decompose like that. So the L in the rotation about orbit direction will be, I will have half m r square omega x hat plus half m r square omega y hat, but m r square omega z hat. And now these guys are not parallel. L arbitrary is not parallel to omega arbitrary. So some the rotation about the principal axis are very important in that case. When you have omega, so in the principal axis, omega is that way about some principal axis. If omega that way, the L is that way. But other than principal axis, it can become a little more complicated and sometimes very interesting rotation phenomena. Okay, so I'm going to try to complete this by doing a couple more examples. Okay, so let's say moment of inertia of a disk. Of a disk. So if you this is a solid disk, not like ring, so we have ring. So what are the principal axes? Well, you just, from symmetry, there will be one perpendicular to that, let's call that z-axis, and then one will be these directions, x and y. And there's a math you can do, and you can find out that if this one is going to be half m, this is r, mass is m, and xy is, xx is I, yy is 1/4 mr square. And you have to set up the integral and do it. So what kind of integral we have to set it up? Well, to do this, you can first notice that z equal to 0 for every point. So you can take a little element here. Over here it will be better, because this is the x and this is the y. So this is a little area element between this is d theta and goes to theta up to that part, and the distance is r. So if you look at this area, and this size is dr. So dr times r d theta, and r is square root of, if the coordinate is xy, then x square plus y square. So izz is going to be dm and x square plus y square, right? So that was going to, dm is going to be how much mass is in that. Well, this is the area. So, and the density is kilogram per meter square now. Rho times dr times r d theta and then this whole thing is just r square. And so now there are two integrals over r and d theta. So r goes from 0 to r, and theta goes from 0 to 2 pi to take into account all the masses, right? So that's going to be rho. Nothing depends on d theta, so that comes to 2 pi, and depends on dr, just 1r and r cube. So let's see, we have a 2 pi rho, and this goes 0 to r to the power 4 by 4, and pi r square rho should be the total mass. So let's see, this gets 2, and so this is half m r square, like this. So that everybody can do this very easily, like we did just now. It's the other ones that are usually hard to do. So let's see how that will go. So we are going to be doing the same thing. So I'm going to try to do say I again, I y y. Let's try to do I y y. Is going to be dm x square plus z square. Now this is 0 because z equal to 0 for all the masses. So dm is the same thing. So dm is rho dr r dr d theta. That dm x is in here, x is going to be just r cosine theta, r square cosine square theta. And you have two integrals, one on the r, one on theta. Now we have a theta integral over here, and theta goes from 0 to 2 pi, 0 to 2 pi d theta cosine square theta. That's going to be pi. You can work it out doing the double integral. So this have rho pi, and I got dr r cube and 0 to r. So that's equal to rho pi r to the power 4 over 4. And so pi r square rho is rho pi r square over 4, and this m r square over 4. So this is the only thing remain, and you should be able to do it. You can do double integral, just like we did for sine square theta earlier. Okay, so some other examples, some other examples are that you should know is about a cylinder. That's going to come up in a lot of problems. So what are the principal axes? You should always say principal axis. It's going to be through the center, let's call it z axis, and this is y, and this is x. So these are principal axes, and this is length L, and the radius is r, and mass is m. So as far as IZZ is concerned, it's just like a whole bunch of disks stacked up, and each one of them, going to be just the same formula, and it's going to be half m r square. Very easy to do, right? It's going to be like just like a disk. So this is like a whole bunch of disks, whole bunch of stacked up disks. Then how about x? Well, that should be equal to I yy, and that is a little bit hard to do because you can see the problem with it. I will not do it here. Maybe I will do it in another video, just this. But there's going to be a combination of 1/4 mr squared, just like the disk, you know, but then because the rod is going to be 1/12 ml squared. Now this separation, how it happens, you probably have to do the whole full calculation. Okay, change my mind. I'll probably just do it now. So you can see that any element here, you can look at any a small piece at say x, y, z of size dx, dy, dz, and try to do it in a cylindrical coordinate. So if you want to have ixx, what will it be? It will be dm y square plus z square. So what's dm? Dm will be rho, this time kilogram per meter cube, and r dr d theta dz. So this is replaces this volume. So in polar coordinate, I'll leave the z alone. Y will simply be r sine theta. And in here, to capture all the masses, you are going to need theta go from 0 to 2 pi, and r go from 0 to r, and z goes from minus L over 2 to L over 2. So now I just need to do this integral. And I guarantee you, I've done the integral, and this is going to be, and m is pi r square L rho. I guarantee that this would be m over 4 r square over 12 m L square. Okay, so that's how you're going to do it. Other extension of this calculation that you may want to try is moment of inertia of a cone. So you can see that you can tell what the principal axis should be for this, right? So one problem often shows up in competitions. Another one is a sphere, and for a sphere, it's very obvious any axis is a principal axis. So you just take any three axes. So this is ixx equals iyy equals izz, and that's 2/5 mr square. And it's worth doing this calculation because you need to do a spherical coordinates. I think it's gone long enough. This is a very long video, and I just wanted to just go over how I look at moment of inertia in terms of principal axis, and how to connect moment of inertia to angular momentum and things like that. Okay. All right. Talk to you later. Bye.